To ensure valid results, linear regression relies on the following assumptions. First is linearity. The predictors and outcomes should have a straight line relationship. Second, independence. Each observation must be independent of the others. Third, homoscedasticity, which means that the spread of errors should be roughly constant across predictors. Finally, a normality. The residual should follow a normal distribution. If these assumptions are violated, our model results may still run, but the conclusions we draw could be misleading or even invalid. We'll talk more about these assumptions when we will discuss the results of linear regression. Under task and utilities, under tasks, under linear models, double-click on linear regression. Now in the middle pane, we will be using the data fhs_lib.heart2 dataset, the one which we created previously, which has the variable BMI. Under roles, under dependent variable, we're going to choose systolic blood pressure. We're going to leave the classification variable out for now. This field is for categorical variables, but we are running a simple linear regression with the continuous variable for this practice. So move on to the next field, that is continuous variable. And let's choose BMI as our exposure of interest or the predictor. So in this case, now systolic is our outcome of interest or the response variable, and BMI is our exposure variable or the predictor variable, or sometimes we also call the systolic as the dependent variable, and the other variables, the exposure variables, we call them the independent variables, because the dependent variable is the value of the dependent variable is dependent on the predictors, which are, at least for the analysis purpose, are independent. Okay, now move on to the next tab, model. And under model effects, click on edit, click on BMI and add it to the model effects. We're going to keep the intercept box, the box next to the intercept, as checked. Click OK. Move on to the options tab. We're going to keep all the default options except the maximum number of plot points, which will change to no limits, as we have done it many times previously. And just submit the code. Okay, so here are our results. What I am going to do is I'm going to save it as a PDF first in my download folder, and yeah, I will replace it. And I'm going to upload this whole file to ChatGPT. So in that case, it should have all the visuals also uploaded there, so I don't have to upload the visuals separately. If not, then we can come back and upload the visuals separately. Okay, so interpret, provide the interpretations. Okay, so let's see what ChatGPT gives us regarding the results. Okay, so here's the structure interpretations of linear regression. SAS output, dependent variable is systolic blood pressure. I'll break it down step by step. Sample size is 5,199 out of 5,209 because there are 10 missing data. This is a large sample giving a very strong statistical power that we already know. Model F value 788, very large value with the P way less than 0.05, even less than 0.0001. So the overall regression model is highly statistically significant, meaning that the BMI as a predictor explains the variation in systolic blood pressure beyond what would be expected just by chance. Okay, R square is 0.1317, which means that 13% of the variability in systolic blood pressure is explained by BMI. Pretty modest. We do not get even 50% R square in health. So from that perspective, 13 is quite modest contribution to the variability in BMI in systolic blood pressure. by BMI. So this is a modest effect size, statistically significant, but most of the variation is explained by other factors, maybe age, sex, cholesterol, and so on, that we already know that there are a bunch of factors which are going to be contributing to the systolic blood pressure, not only the BMI. But anyway, 13% is a substantial contribution to the take it this way, that if somebody controls the BMI, he reduces his chances of high blood pressure by 13%, right? And of course, they have to look after the other things also, the cholesterol and the diet and exercise, and in some case, you might have to start even the medicine, but still. Moving on, the adjusted R square is almost the same because we only have one predictor here. When we increase the number of predictors in the multiple linear regression, including age, sex, cholesterol, multiple factors, then we would see that the R square and the penalized version of R square, which is also called adjusted R square, are going to be continually, this is the average error of prediction, 22 millimeters of mercury. It is going to be different, is different. Anyways, leave this, is not important. Moving on. Intercept is 84.99, p-value is 0.00. So this is our beta naught. Represents the estimated systolic blood pressure when BMI is equal to 0, while not clinically interpretable. No one has a BMI equal to 0. It is a necessary anchor point or the starting point for the regression line. Here is the most important value for our analysis, 2, which means that with each unit increase in BMI, systolic blood pressure is estimated to increase on average 2 millimeters of mercury, holding other factors constant. We do not have any other factor included, but it is anyway linear regression. The statistical analysis package, SAS, is assuming that we are holding the other factors constant. Excuse me. This is a strong clinically relevant positive association. There is a significant positive relationship between BMI and systolic blood pressure. People with higher BMI tend to have higher systolic blood pressure. So we already have interpreted. And it is even giving me the plain language summary of our results. It has not given us separately the interpretation of the visuals. So I'm going to just copy these visuals separately and paste them on ChatGPT, and let's see what it tells us. Okay, so this is our first visual about the predicted for visuals. Okay, this was observed versus predicted. The predicted value is the one which is on the line, and we see that there is a high variability in the observed values of systolic blood pressure based on BMI. Most points are clustered around systolic blood pressure over 120 to 160, which matches the expected population distribution. This is noticeable vertical spread around each predicted value. The predictions are not exact but have substantial errors. Some outliers are visible. Interpretation. The clustering along the diagonal indicates the model is capturing the overall trend. Higher predicted systolic blood pressure corresponds to higher observed systolic blood pressure. However, the wider scatter shows that BMI alone is not strong predictor. Okay, this agrees with the R square of 13%. Okay, let's move on to the next visual. In this, not all of them are important, but we will like to have ChatGPT interpret all of them. Okay, the most important of them is the QQ plot. So let's jump to the QQ plot directly here. QQ plot, let me show you. This is the QQ plot, which shows that if the values are normally distributed or not. Okay, so the points deviates from the straight line, especially at the tail, suggesting that residuals are not normally distributed. Okay. And the histogram of residuals is roughly bell-shaped but slightly skewed with long tails. Okay, so overall interpretation, this model is statistically significant. Normality assumption is violated. Residuals are not normally distributed. Homoscedasticity assumption is violated. These issues do not invalidate the finding, but they suggest that BMI alone is insufficient and other predictors need to be added to improve model accuracy. In fact, let's interpret the one more visual and then we'll get to the next step. This again is an important visual, so let's get the interpretations. Okay, the line slopes upward, indicating positive relationship between BMI and systolic blood pressure. As the BMI increases, the systolic blood pressure increases. Okay, confidence interval is 95%. Okay, there are a narrow middle, widened at the extreme. So let's get to the bottom line. This fit plot shows that the relationship between BMI and systolic blood pressure. The upward sloping line indicates that higher BMI is associated with higher systolic blood pressure. On the average, for each unit increase in BMI, systolic blood pressure with 2 millimeters of mercury. The shaded area represents 95% confidence interval for the mean prediction, while the dashed line shows a 95% prediction interval of individuals. Notice how the data points are widely scattered around the line. BMI explains only 13% of the variation in blood pressure, meaning other factors also play a role. Okay, so next we can even ask ChatGPT to write an article, write a scientific paper based on all these results. So I'm just gonna do exactly that. Can you write a scientific paper based on the above results? Okay. It is not going to be a high quality, but at least it's gonna give us some baseline for us to include our human expertise to the paper. So as far as the statistical analysis is concerned, interpretations are concerned, ChatGPT is exceptionally good with almost 100% accuracy. It can give us the interpretations accurately. But when it comes to more creative things like scientific paper, then that's where so far ChatGPT is lacking a lot. So in that case, human intervention is required. So background elevated BMI is known risk of hypertension, yet the extent of contribution is unknown. Objective to examine the linear association with BMI and systolic blood pressure in large community. Method we analyzed, blah, blah, blah. Results, the BMI was positively associated with And conclusion, higher BMI is strongly associated with systolic blood pressure, though BMI alone accounts for a modest proportion of variability. These findings reinforce BMI as a key but not exclusive determinants of blood pressure. Future model, blah, 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 will be required. Okay, so they're very interesting. See you in the next video.